Hello, today I'll be talking about the piezoelectric materials and all of its implications. First of all, we need to understand what piezoelectricity is. It is described as an electric polarization in a substance resulting from the application of mechanical stress. Piezoelectric materials are a key component of what are considered smart materials, which are materials whose properties change in a controlled way in response to external stimuli. Figure 1 explains how piezoelectricity works. In equilibrium, the charges of the unit cell are distributed in such a way that there is no net dipole moment. B, when compressed, a net dipole moment arises in a vertical direction. And C, when stretched, a net dipole moment arises in the horizontal direction. Piezoelectric effect means that when the material is subjected to an external force in a fixed direction, the internal phenomenon is generated, and at the same time, opposite signs are generated on one of the two surfaces. When the external force is removed, the crystal returns to an uncharged state. A piezoelectric transformer works by converting electrical input to magnetic energy and then reconverting that magnetic energy back to electrical output. This mechanical conversion is achieved by a standing wave vibrating at a frequency ranging from 50 to 150 kilohertz, as seen in Figure 2. Figure 2 shows how a Rosen-type piezoelectric transformer works. It works in a high set of voltage ratios, where an input voltage creates a mechanical vibration in the primary section. This vibration is then transferred to the secondary section, where it generates an output voltage. This transformer, due to its high voltage generator, is used in CCFL backlighting, which are panels in laptops. Now, there are various materials that qualify as piezoelectric. However, I will focus on the piezoelectric materials used in the biomedical field. To meet the requirements of biomedical applications, piezoelectric materials should possess high electromechanical coupling and good biocompatibility. Piezoelectric materials for piezoelectric uses are classified in three, which are ceramic, polymers, and biomolecular materials. In case of zinc oxide, it is a crystal structure directly correlated with its piezoelectric effect, as it allows polarization vectors to rearrange along the direction of the electric field. In the case of polymers, some flexible polymers exhibit this ferroelectricity and piezoelectricity by stretching, which results in an electrical polarization via molecular dipole reorientation. For biomolecular materials, they generate a surface charge polarization, allowing for tissue growth and regeneration, also implantable sensors. I'll be talking about the specific piezoelectric materials on the same crystal structure that is perovskite. The perovskite structure is a specific crystal lattice with a general ABX formula, where a large A cation occupies corners. The smaller B cations are centered within the octahedral of X anions. When an electric field is applied to PCT, it goes through a mechanical deformation, leading to a piezoelectric effect. This opposing energy conversion happens because of the material's non-centrosymmetric crystal structure, where the stress causes a shift in the positions of positive and negative charge centers within the unit cell. Its high electromechanical coupling ability is used in ultrasonic sensors, and as seen in picture 3, the piezoelectric effect in this case is described by the movements of the ions in the crystals under stress, resulting in changes in the balance of ions, where the material is at a non-centrosymmetry and is at non-equilibrium, becoming piezoelectric. This is my model of the lead synchronate titaniate. And another piezoelectric material that has this perovskite crystal structure is barium titaniate. This is a ferroelectric material, meaning that it exhibits a spontaneous electric polarization that can be switched by an external electric field. The ferroelectric behavior happens from the displacement of titanium ions in the crystal structure, as shown in Figure 5, creating a net dipole. The specific material changes shapes as temperature decreases, increasing its piezoelectricity as the titanium ions become displaced. Additionally, when an external mechanical stress is applied to the material, there is a displacement of charged ions. This additional displacement also leads to a change in the overall polarization of the material, generating an electrical charge. The ability to transform audio signals into vibrations that produce sounds is the main reason why barium titanium is used in microphones and speakers. This is my SolidWorks model of barium titanium. So the lattice structure of barium titanium in a single perovskite crystal structure. And figure 7 also shows the same structure, but this time showing the titanium ion, the green sphere, in the center. Other applications of piezoelectric materials include tumor therapy. As shown in Figure 8, the procedure conforms with a two-step collective therapy where the materials generate electrical signals through the ultrasound and X-rays mechanically stressed to kill the cancer cells. First, the nanocatalysts are injected into the tumor, and with ultrasound waves stimulating the material, electron hole pairs are created, and this drives these redox reactions. So this further causes oxidative stress damaging, uh, ending up damaging the cancerous cell. In sequence to the X-rays further stimulate the materials, damaging the DNA, pushing the cells finally into apoptosis. This is my work cited. Thank you.